Really good clocks are quickly becoming the key to building bigger and more performant distributed databases, but it wasn't always this way. Actually, for the longest time, using physical clocks in distributed systems has been a cardinal sin, and most engineers today would tell you not to rely on them. That's partly why NoSQL databases have grown so popular in the last 20 years. But now that's finally starting to change, so grab your hymnals for this one, because it's time to talk about time. Before we jump in, if you're new to this channel, hey, I'm AJ. I'm a staff engineer at Datadog, and I'm an AWS hero. This channel is all about software performance, cloud computing, and distributed systems. If you like these types of things and you want to know when the next video comes out, hit that subscribe button. All right, so in the beginning, we had a database, and it ran on a single node. And this is great. If your system scale and reliability constraints fit on a single machine, you should consider staying that way because you get some great properties right out of the box. The benefit of this type of system is consistency, which is the C of CAP theorem. You may have heard of it. Basically, it means that every read receives either the most recent write or an error. Let's show you what I mean. So in a consistent single node database, the big benefit we get is that anytime a write happens, any read that immediately precedes it will always get the results of that last write. And it looks like this. If we have a writer come in and they say, okay, I want to set x equals 5. Now at this point, if any other reader comes in, or literally the very next request, the next millisecond or even microsecond comes in, they're going to read this and they're going to read back, okay, next request says x is 5. This is great. And the reason this works is because the database is running on a single machine, so data doesn't have to be synchronized anywhere. We can protect access to the x value using something like a mutex, which you're probably familiar with. That will exclude other writers, and then we can have one write to x, and then the next one happens, and that's fine. If it updates, it doesn't matter. The benefit here is that exactly one thing can change at one time, and we don't have any kind of delay of the network involved. But eventually, we wanted to build a more robust and resilient service that could serve more users, which meant we would have to run this database across more than one computer at a time. We needed to build a distributed system. Now, I want to be clear, if you don't need the throughput or reliability of a distributed system, you probably shouldn't build one. But there are a bunch of benefits, and the biggest is that the reliability of your system will grow exponentially even though costs only grow linearly. This is because the chance that any single node in the system may fail is low, but the chance that all nodes, or at least a quorum of nodes in the system, fail at the same time is infinitesimally smaller, and it shrinks with every additional node in the system. It gives you a more reliable system at a linear cost increase. So here's a look at the first distributed database you may encounter in your career. Maybe it's a Ruby on Rails app or Laravel or something. This is like a replicated Postgres or MySQL service. And the way it works is you have one primary node that receives all updates or creates, like, all writes go to that node. And then it actually writes out a stream of changes to replica data stores. This is a really useful architecture and can work really well, scale really large, especially for read-heavy workflows. If you don't do a ton of writes, you're mostly doing reads, then this is fantastic because all of your writes are still coordinated by a single node, so you don't have to worry about distributed transactions, which we're going to talk about in a bit. But you still get the additional scale of having all these replica readers, and if the primary node goes down, you can fail over to one of those replicas. It's a clever system, and it scales really well for a long time. So let's take a look at what a replicated Postgres system kind of looks like when you write to it. Now, the write comes in, and it has to go to this primary node. It must go to the primary node. And it says, I want to set x to 5. And at this point, it might come back right away. You have a lock on that transaction. You can just make it happen, and you can say, okay, that's great, no problem, x is 5. Now, this has to get replicated to these replica nodes, and this process is asynchronous. This is either done with block-based replication or with a stream of updates on a log. And what's happening is that the primary will say, okay, I just committed x is 5 at this certain value. And it says, okay, now I have to go and push this down to my replicas. One downside of using a replicated Postgres or MySQL database in your application is that there can be replication delay between the primary and replica databases. This means that a user can come along and request the value of x before the primaries had a chance to push data down to this replica. And in that case, the response comes back and says, oh yeah, I know x is, maybe it's 14, right? And now this user has incorrect information. Now, this is fine. In a lot of cases, a user can refresh the page or retry, and maybe if they're going to write something, they'll have to write to the primary node anyway. But that begs the question, what happens if our throughput is too big for a single primary node? Now we have to consider how we can build a database which runs on multiple computers, but it feels like it's one big database. We want a distributed system which can give us a consistent read where any write to the system will appear all at once to any query, regardless of which node that query hits. Now we can build a system which allows multiple nodes to receive writes, but we still need a way to exclude other nodes from modifying data that we're about to modify. That's known as like a pessimistic or two-phase locking concurrency control. And the way this works is kind of simple. This write comes in and we say, okay, I want to modify X. And it says, okay, node 1 receives this request, and it's going to go to node 2, and then it's going to say lock X. It'll go down to node 3 and say lock X. And as long as these two nodes are all in coordination, they know that now they can't update X at all. So now node 1 says, okay, go ahead. And then the user comes in and says, okay, we're going to set X to 5. And at this point now, node 1 can commit it, and it can broadcast that commit to all these other nodes to have a quorum. And any other transaction that was trying to occur and talk to either node 2 or 3 would be locked out or prevented from running. This is great. It means that only one transaction can run at a certain time, which we need. And this works, but it's slow. Sometimes another read to node 2 or 3 is just that. It's a read. It won't be followed by an update or anything. Or sometimes a user writes a really big transaction. It locks a lot more rows than you need to. A faster way to do this is to be optimistic and to hope those transactions won't conflict and then abort any that do. One form of optimistic concurrency control is called serializable snapshot isolation, and it works a lot like regular snapshot isolation. When a transaction begins, it operates against a snapshot of the current data in the database so that the transaction can work against a consistent view of the data. Once the user's transaction completes but is not yet committed, the database checks to see if any conflicting transactions have been committed. If so, the uncommitted transaction will roll back and the user must retry it. Here's what this looks like. The user request comes in and says, I want to modify X or possibly or probably multiple rows, right? X, Y, and Z. And what node 1 will do is we'll return a picture of what those values are at the time. Okay, so X is currently 7. And now at this point, my user can make their transaction against that information, even though some other user may be running an update, maybe updating other data in the same row, or even that data itself. It may or may not conflict. We don't know yet. And then what will happen is this write will then say, okay, we're ready. We're going to set X equal 5 and then commit. And now at this point, these nodes will coordinate and decide whether or not this transaction conflicted or not. And if it did, it'll roll it back. And then if not, it'll be committed and then it'll be synchronized around. But therein lies the tale. We have a distributed database. How do we know that another transaction has even conflicted with our running transaction? How does our node even know that another one occurred? There are two ways to do this. We can use what's called a logical clock, like a Lamport clock, or we can use regular clocks, which, like I said, they've been a sin to use regular clocks for coordination like this up until recently. Lamport clocks work by requiring the cluster to coordinate and hand out monotonically increasing version numbers for each individual item, maybe a row or a cell in the database, however you want to model it. If two writes or a write and a read are colliding, whichever transaction has the highest logical version number wins. The last write wins. So here's how this works. The user comes in and says, I want to open a transaction and I want to modify X. Then the node will respond with X is 7, but the version for X maybe is 100. So this is the latest version node 1 knows about. Now when the user wants to modify X, they're going to say, okay, X is 5, and we're going to respond version equals 100, commit. Now at this point, node 1 will check to see if anybody has a higher write for X greater than 100. Any X.version greater than 100. And the same thing will occur here. And if these nodes, either of them respond no, then that transaction will be allowed to commit because nothing else has modified X. And if the answer is yes, actually node 3 has maybe processed transaction 101 or 102, then this transaction will roll back and the user will have to come back, fetch new data with an updated version number. And this works great, but this requires coordination. Coordinating slows down our system throughput. It means we have to communicate constantly. We're constantly bouncing version numbers back and forth and keeping data up to date. So how about we tried using a regular clock? Then we could assign just timestamps to transactions and detect when an older transaction, which is defined as having an older timestamp, has occurred. And then we can abort if a newer one is committed. And that totally works. It can work great, especially when everything is working well. But clocks aren't perfect. They can drift. They can disagree with each other. Two computers in the same system could have totally different clock readings, and that can really screw up our database if we're relying on that for consistency. So it's time to open our books to page 291, where we can learn about the pitfalls of trusting clocks. All right, so here's the example from designing data-intensive systems. We can see that it's the exact same system we were describing, right? We had a 3-node cluster, and in this case, we have 2 clients. Now, client A comes in, and they talk to node 1, and they say, okay, we want to set X to 1, and at this point, the clock for node 1 is at 42.003. Totally fine, no problem. The node responds, okay, we're going to commit, and at that point, it was 42.004. Now, this transaction has to be synchronized with the rest of the data system. The problem occurs when client B comes along and talks to node 3 and says, I want to set X to whatever it was, plus 1. The problem is that node 3's clock is behind. It's behind node A's clock. When, according to node 3, this transaction occurs, it's 42.003. But this transaction, which actually occurred earlier in real time to node 1, happened at 42.004. So this user gets a message back from node 3 saying everything's okay. But when the database has to go back and reconcile these transactions, the problem is that client B's write occurs before client A, even though in real time, client A's write occurred first. So if everything was right and happy here, the value of X after all these transactions would be 2. The problem is that node 3's clock was behind, so it made it seem like client B's write happened first. So it effectively deletes client B's write because client A was resetting X to 1. So instead of X being 2, the value going forward in real time is X is now 1. Now this problem with write skew is why distributed systems engineers have considered it a sin to use clocks for consistency in distributed systems. It's just too big of a risk. If they have write skew like this, the database is totally useless if we start dropping data. But what if we had some kind of super accurate global clock? Now we could just use these transaction timestamps just like they're doing here, but we know it would be perfectly ordered. We know that everything that happened in real time would be what happened in server time. Then we could assign timestamp to transactions like they do here and have full confidence knowing that the order or the causality of the system is going to be preserved. It's important to note that if these clocks were to fail, write skew could still creep in, and that is why these clocks are a single point of failure in a distributed system. In Google's case for Spanner, their true time system uses both GPS-based clocks and redundant atomic clocks to ensure that the system is always up. They actually call this the Armageddon failover mode if they have to fail over to these atomic oscillators because the GPS system was taken out. So for decades, it's been a distributed system sin to rely on physical clocks in lieu of coordination for consistency. But Google's Spanner first showed that this was possible. And now Amazon Aurora DSQL is using even more precise clocks to get even tighter boundaries on transaction timestamps. There's even this new paper out this week from Huawei about a system called GaussDB, which is similarly based on highly accurate GPS-enabled clocks. This is why I'm so excited about new clocks being available in places like AWS, where all EC2 instances can now use Amazon TimeSync service to get single-digit microsecond clock accuracy anywhere they're being used in the world. Now, improved database consistency is only the tip of the iceberg for the applications of highly accurate, globally synchronized clocks. Mark Brooker's blog post called It's About Time sheds even more light on the possible applications here, including improving observability, being smarter about cache time to live and expirations, rates and leases, and more. It's truly only the beginning here for this type of foundational technology, so I can't wait to see what other applications we start to see of these globally accurate, super precise clocks. Whether you're a distributed systems developer, an enthusiast, or you're just an engineer that likes using really big databases like PlanetScale or Spanner or Aurora DSQL, it's a really exciting time to be using these systems because they're continuing to get better as this hard and fast rule about clocks is starting to fall apart. I hope you liked this video. If you did, hit that like button and leave me a comment below letting me know what you want to see in the next one. See you then.